In this video we're going to look at another type of transformation, another type of linear transformation called a dilation. So let's start with a sketchpad command. Let's start by making us a nice little pre-image here, maybe a little triangle that we might color blue, and let's give these guys some names. Okay, and then what we need is a point here that's going to be the center point. I'm going to call it center. Okay, and then we need a dilation factor. Let's do that by parameter. And this is just a number. Let's make it 2 to start with. No units on that. Okay, so the way you work this in Sketchpad is you click on the center, you go to Transform, Mark Center, just like you would for, say, a rotation. Then you click on Factor and say Transform, Mark Scale Factor. You select your pre-image points and do Transform, Dilate. And that gets us our new points there, which is our final image. Now notice something very different this time happened from the examples that we looked at in the past, and that is that this dilation gives you something that is not congruent to the original. So there's the image B prime, A prime, and C prime. Okay, so do you see any relationship about what's going on here? Do these look congruent? Well, clearly not congruent, not the same length, but as I move the center around, do you notice anything about the points here? Well, what would happen if I connect up with, say, with a ray, the center to the pre-image point here? And then center to pre-image and center to pre-image. Look what happens. The image point is on that same ray. Isn't that interesting? Let's see if that works out. This center could be a point in the interior of the figure here. It could be at a vertex of the figure. Oh, that's interesting. Notice which point doesn't move. If it's actually on, the center appears not to move at all. It's a fixed point. Okay, could be on the side of the figure, could be outside the figure out here. Okay, well, what does the scale factor have to do with anything? Well, what if I make the scale factor 1? Oh, that's the identity transformation. Okay, let's put it back to 2. What if I make it in between, 1.5? Oh, interesting. Or what if I make it, let's go back to 2. Okay, so maybe I better show some more digits here. Okay, now let's measure some distances. Let's go from the center to A, measure that distance. Maybe instead of calling it center, I'll just give it a one-letter name. We'll call it X for the center. But X is the center. Okay, and then we'll go from X to A prime. Interesting. Okay, put that over here. Okay, and let's go from X to B, and then X to B prime. X to C, and from X to C prime. So these are all distances from the center to the image, red image, and these are all distances from the center to the pre-image. What do you notice about these guys? happens if I take this and divide it, calculate that guy divided by this one, that's 2. Or calculate image distance divided by pre-image distance, 2 also. Calculate image distance divided by pre-image distance, hey, that's also 2. And in fact 2 was what? The scale factor. What if I change this to 3? Okay, so that's what the scale factor is doing. So at the moment what we have is every distance from the center is 1.5 times the distance that originally was. So in other words, let me say it more precisely. We measure the distance to the center from the center to the pre-image point, and we multiply that distance by the factor, the scale factor. Then we get the distance from the center to the corresponding image point. Interesting, huh? And that's what we call a dilation. Now it turns out that you're going to get, well, let's see what we get here. So if we'd have, let's measure the distances this way, from A prime to C prime, from A prime to B prime, and from B prime to C prime. So those are all distances within the side links within the red image set. Okay, let's do the corresponding ones here. So if we measure from A to B, that would correspond there. And from B to C, there, and from A to C, there. Those are all distances within the pre-image. And once again, if we divide, look what happens when we divide out the red divided by the corresponding blue, and do the same thing here. So these are the ratios of corresponding sides, and in fact, look what happens, they're all the same as the scale factor as well. So it's defined, we're actually going to define this in terms of the condition that we first saw, defining a dilation, but it turns out that what it gives us is sides that are proportional. Well, we know we have a theorem about triangles that says if the sides are proportional, guess what happens? The angles are all congruent, and in fact these two triangles are, what do we call them? Similar triangles. Yeah, they're not congruent triangles necessarily. They'd only be congruent triangles if the factor is 1 and it's really the same triangle again. But if the factor is anything else, we're going to get similar triangles. If the factor is larger than 1, then the image is bigger than the pre-image, and the points are in the order center, pre-image, image. Center, pre-image, image. Center, pre-image, image. In other words, the pre-image is between the image and the center. But look what happens if the factor is less than 1. Now the image is smaller than the pre-image, and the order is different. It goes center, image, pre-image, like that. The pre-image is the one in the middle. We can talk about a negative factor here, but this is not. This is a little bit different. This gives us, well, a factor of -1 gives us something we call an inversion. Okay. And so we get something a little bit different going on when we have a negative factor. So right now we're going to restrict our attention to positive factors, like that. So these are called dilations. Here's one where the dilation factor is given by a slider, and it does allow negative dilations, negative factors, which is not quite a dilation. And of course there's your center point. So look what happens with the dilation. Everything in the image, every length in the image is the dilation factor times the corresponding length in the original. So this is from a couple of different ways. That by definition, the distance from a pre-image, from the center to the pre-image, if we multiply that distance by the dilation factor, we get the distance from the center to the image. Okay. But it also turns out that corresponding sides here have the same factor. So again, what if I take this back down to 3 just to make it easy? Get a nice whole number, 3. Okay. Then this length is 3 times that one there, and that length is 3 times that, and that length is 3 times that. But remember, if you have if the lengths are 3 times as much, what happens to the angles? Well, they're actually the same. So if we were to measure corresponding angles here, we'll find out that those are actually congruent angles. So this is a conformal map, means it preserves angle measure, but it is not an isometry. It does not preserve distance. It is, however, a similarity transformation. So it's not an isometry. It's not an isometry, or it's not a congruence transformation, which are the isometries, but it is actually a similarity transformation. In fact, if you take all similarity transformations, all transformations that map a pre-image to a similar image, they actually turn out to be the composition of a dilation with an isometry. You could do an isometry or a series of isometries first, and then a dilation at the end if you wanted to, and you can always get the similar figure that way. So, for example, well, in this case, you can do it with a single dilation. In some cases, it requires it might require a reflection or rotation or something along with it. Okay, here's one over here where it's done by parameter, so I can put in the scale factor here. This is kind of like the one I did on the other page. Okay. Notice that this triangle here is twice the size of this one in terms of lengths. It is the same size as that one in terms of angle measurements, but it is 4 times as big in terms of area. And in fact, if you look at this, I actually have 4 triangles here which are actually congruent to the original triangle, and so they're equal in area there. And so you see it's 4 times the area. Is that still 4 times the area? Well, no, that one's even bigger. So let's remember something about, let's just start with the rectangle to start with. If we have a nice little rectangle here that has some base and some height, we'll call it base 1, height 1. The area 1 is base 1 times height 1. Now let's look at a size transformation here. Let's make it maybe 3 times as big. And notice I can do this on the grid here. So since this is 1 tall, this one's going to be 3 tall. This is 2 wide, so this is going to be 3 times that 6 wide. Okay, but anyway, let's say we have some dilation factor f. In this case, f is 3, excuse me. And so we get a base 2, which is just f times base 1. And we get a height 2, which is just that f times height 1. So our area 2 is base 2 times height 2. But base 2 is the factor times base 1, and the height 2 is the factor times base 2. So that is the factor square times base 1. Let's see, this is a height. Base 1 height 1. Let me say that the right way. Factor times base 1 is base 2. Factor times height 1 is height 2. And so this is factor times base 1 height 1, but base 1 height 1 is area 1. So So area 2 is f squared times the area 1. So in other words, this one is actually, if you look at this right here, the sides are 3 times as long. So if that's 2 and this is 1, this one is 6 and this is 3. But in fact, we don't get 3 times as many rectangles inside in terms of area. If you look, we're going to actually get 9 times as many rectangles on the inside. So it's 9 times the area, the factor squared. Right at the moment I have the factor of 3. Well, this works in general for any figure, not just rectangles. You know, so you could go through the same kind of argument for triangles as well. But it turns out that it's a factor of f squared. Now, if you make this three-dimensional, then what's going to happen? Let's just take a 3D figure here. Okay, so we have a base 1, height 1, and let's say a width 1, or depth 1. Okay. Okay, well, it's going to be the volume. Base 1, height 1, width 1. And if we could do this, we could do a three-dimensional scale factor. You know, maybe make everything twice as big. Okay, so what's going to happen? This is F times B1. This is going to be F times H1. This is going to be F times W1. And so volume 2, F times B1, F times H1, F times W1. And so that's going to be what? F cubed times B1, H1, W1, which is F cubed times volume 1. So it multiplies it by cubing. It cubes it. Interesting connection there. So this is called a dilation. Okay. Okay. So how can we go about constructing this? Say, we've seen how to construct it in Sketchpad. How about a compass and straight edge construction? Okay. Now this is, I'm going to illustrate this with a factor of 3. If the factor is a whole number, then this is a pretty easy construction. So let's take a look at this example. So O is going to be the origin or center of our transformation, and here's our figure ABC triangle, which is going to be our preimage. So first of all, to find A prime, we know that it's going to be somewhere on that ray going from O through A. If the factor is bigger than 1, A prime will be out here further than A from O. If A factor is less than 1, it will be between O and A. So we need to be 3 times as far out. Well, all we have to do is set our compass to the distance from O to A, make a little mark here, a little piece of this circle. Then from there, move the center out here, make a little piece of this circle to find point D. And all we need is a little mark right there. And then another one back here, and a little mark there. Notice that all 3 of those have the same radius, the same as the distance OA. So the distance from O to A prime is 3 times as much. And now we have A prime. And we could do the same thing for B and for C and connect up our final points there. So there it is for C. Here it is for A. Here it is for B. Or here's everything. Now, of course, when you show everything with these, when you draw the full circles, things do get a bit messy. Okay, the way to avoid this, of course, is when you're doing this by hand, is you don't have to put this full circle. You just need to, well, really the first one, you just make a little bitty mark here, just a little bitty one right here to show how far you went out for A, a little bitty mark here to show how far you went to D, and a little bitty mark here to show where A prime is. Okay, and similar for the others, and it's not nearly as messy when you actually do it by hand. And that's the construction. Now, if this is any natural number, that works great. If you wanted to do a factor of a half, we know how to bisect a segment with compass and straight edge, so we could do that. If we're allowed to use a ruler, then we could compute the distance, we could measure the distance O to A, and then just multiply by whatever the scale factor, whether it's a decimal or fraction or whatever, and then approximate at least what the distance is to A prime by measuring it out with a ruler as well. So that's a different type of construction there, using a ruler as well. This is a classical construction using compass and straight edge. Now, different factors makes it's more difficult if it's not, say, a half or just an integer. You know, if it was like 2.7 or something for the factor, that would be a little harder to construct. But at least for our whole numbers, they make pretty nice. So let's look at a grid. Again, if it's a scale factor that's pretty nice number, like a whole number, we can figure this out. We need a center of our dilation. Let's say we put it, we could have it at a point. If we do, the point D prime is the same as D. It could be at some point on the figure. Let's see, let's give us a couple lattice points there. It could be a point on the figure there, or it could be in the interior, it could be in the exterior, it could be any one of these. But let's say we put it, right there, let's say. Okay, so it's pretty easy if the factor, let's just say in this case the factor is 2, I can change that dynamically, but let's say it's 2. To find A, notice I go right 2 and up 2. I just double both of those, so I'm going to go right 4 and up 4. So that's going to put A prime right here. I'll just put it on there. Right 2 and up 2, I go right 2 and up 2 again, so there's A prime. D goes straight left 3, so now I go straight left 3 more to 6 out. And so connect those up, we've got A prime and D prime, so we can connect those up to get AD. A prime, D prime, the line segment. Now this one goes left 2, down 2, so I go left 4, down 2. So there's C prime. And D is down, let's see, down 1, 2, 3, 4, so I go down 8. 7, and 1 more. Try again. 1, 2, 3, 4, 5, 6, 7, 8. And instead of left 1, we go left 2. So those are the ends, and so that gives us an image. Now we could check. Notice I didn't do any compass and straight edge construction here. I actually used the grid itself, and we just did it by counting out here. And so notice that we could kind of check it though to see that those rays do give us the right thing. For some reason I don't have the 1 through C and C prime, but you could draw that ray as well. And so we see that those all work out. Now let's leave the scale factor 2. Look what happens if I say put it on a vertex here. Okay. Get rid of some things here. Okay. That point's going to be fixed. What if I put it on a point that's on the, oops, let's leave that. It's the center I want to move. What if I put the point, let's see, on a side? There we go. What if it's outside the figure? There's another example. Okay. What if the factor is something besides 2? What if it's 3? Now we're tripling everything. So this goes to the right 3, now it's going to go to the right 9. 3, 4, 5, 6, 7, 8, 9. This one goes right 2, down 2, so it's going to go right 6, down 6. So you just triple both delta x and delta y. You can actually, if the factor is something, a factor of a half is not too hard to do. You do have to estimate some of these a little bit, but if you'll draw in these radial lines, that can help you. So here, this goes to the right 3, so I do half of that, I go to the right 1 1/2, so we can get it pretty close there, halfway between the grid lines. This one goes to right 1 down, let's see, go right 2 down 2, so that's right 1 down 1. That's a nice lattice point there. This one's right 1 down 3, so that's right 1/2 down 1 1/2, and so forth. And you can get those relatively close. What if I do 1 1/2? So this is right 3 3 times 1.5 is 5.5. 4.5, excuse me. 4.5. Right 2 for B times 1.5. That's going to be right 3. So it goes here. And so forth. You can work that out. Okay? Can we get this with a single transformation here? Well, clearly it's not an isometry. Perhaps it's a single dilation. Well, we know that if we just connect up pre-image to image point with a line, that's going to be the where those lines intersect, that's going to be the center of your transformation. So since those all do intersect in a single place, that will be a center of our transformation, of our dilation. Okay? Now, what if we want to find the scale factor? Well, we just find some lengths and divide. So we measure from the center to A, that's this distance, and then from the center to A prime, which is this distance, and divide, and we get the scale factor, which in this case is 3. Okay, so somewhere back in the background I'll probably have a scale factor of 3 hidden if I did that. Let's see, where is it? Okay, I probably just did it without a parameter. I did it by just say transform, dilate, and actually put in the ratio there. So you can do a fixed ratio there. Okay, so that is a dilation, also known as a size transformation. That is a basic similarity transformation.